Okay. Welcome everybody to the session on Kolmogorov complexity and one-way functions. We have 5 talks. The first 3 about Kolmogorov complexity and one-way functions, and the next 2 more about the one-way functions than the Kolmogorov complexity. The first is lower bounds for Levin Kolmogorov complexity by Nicholas, and Nicholas is going to give the talk.
Yeah, so thank you. Hello, everyone. I have the honor/duty to introduce Kolmogorov complexity since I'm the first speaker of the session. So I'll start Goldreich style. Let's see, okay, this works. So since you're in the Kolmogorov session, we need to talk about Kolmogorov complexity. I'm simplifying a lot here for the sake of the presentation. Here, we just say the Kolmogorov complexity of the string x is the minimum size of any program, whatever program means to you, such that that program produces that string given the empty input, for example. We don't care about running time here. It's just, you can think about Kolmogorov complexity as essentially the smallest compression that you can come up with for a given string, right? And this particular talk, and also Shuichi Hirara's talk, is going to be about a notion of Levin's notion of Kolmogorov complexity, which he introduced 40 years ago now. And this version is a resource-bounded version of Kolmogorov complexity in the sense that we don't only take the minimum of our programs of the length of the program, but we also account for the running time of the program. So if this program pi produces x in t steps, then we charge log t for this program, right? So we take the length of the program plus log of the running time. Now why log? Well, log, this comes from some universal search application. We don't care too much why it's log here, but just remember this because it will also come up in another talk. This is the version that we care about right now. And just to be really Goldreich here, we also define the decisional problem, which is just the tuple of all strings and complexity thresholds, such that the Levin complexity of that string is lower than the threshold. Okay. So this talk is about the hardness of this particular Levin KT notion. And so I'll show you this little picture here. I'm essentially summarizing the previous results on KT. Why do we care even about KT? Especially the hardness of KT. And one reason is that Yan-Yi Liu and Raphael Paz, they essentially relate the hardness of KT to several, well, essentially 2 interesting complexity theory and also crypto applications. Namely, if MKTP, so hardness being up here, so if KT is more upwards, then it's harder. And this particular class here is heuristic BPP, which means it's the class of randomized polynomial time algorithms, where you can have a 2-sided error. So it's an average notion, and you can make false positive and false negative errors, like a small fraction of them. And if MKTP is in this class, so it's below this bar here, then there's no one-way functions. And they also showed that if it's below a certain other class, which is average BPP, then BPP is equal to x, which means essentially that randomness can allow you to do exponential computation, which we don't believe is true. So this is the reason why we care about the hardness of KT, because it has major implications, right? And they got the best paper at Crypto for this. Now there's this thing called algebraization barrier, so we cannot hope to show this unconditionally with the current techniques, because, well, you would need non-relativizing or non-algebraizing. So here, algebraizing is just a more fancy term for relativization. If you don't know what algebraization is, just think of relativization. So we cannot hope to show that MKTP is above this barrier here. What we do know is that MKTP is above this bar here. So this is P uniform ACC0, which is just some particular type of circuit class, right? You don't need to worry about this concrete class. It's just some type of specific circuit class, and we know that there's no circuit in this class that computes MKTP. And this is a really strong result. It's actually an immunity result. I won't go into that because of the time constraints, but I just want to mention that Shuichi Hirahara showed this 4 or 5 years ago. And now this talk is about the first lower bound against the uniform time class, about linear time in particular. If you don't, like if you're in a particular model where you have a universal constant time simulation, then you can actually increase this to be a quadratic lower bound. So we're going to show that, well, I'm not going to show it, but that's a result of the paper, is that MKTP is above this bar, and these two bars are not comparable. So I'm going to plant the question here is like, what if, can we increase this to exclude P? And notably here, P is below this algebraization barrier. So even if we show that MKTP is not in P, there's no major consequence of that. Right. And then I also want to mention that Ren and Santanam, they provide an oracle relative to which you can approximate KT to within some constant, multiplicative constant, and still BPP is equal to exp. And this is seems quite counterintuitive to our result, but I'm going to leave this as a question. So simple diagonalization for normal Kolmogorov complexities is just an entry-level argument, because I can't really explain the full technical details of the papers. I'm just going to do a toy example. So suppose we have a Turing machine of some constant size, which decides the Kolmogorov random strings. So that's all the strings that have Kolmogorov complexity more than the string itself. And then we just assume, for the sake of the presentation, this program can compute its own size. And then we just iterate over all strings. And then if we find a string that's longer than C, we output that string. So what that looks like is we start at the empty string, we go row by row through all of the strings, and then eventually we will find the string X, which is longer than C, and then we'll output it. Because our condition that X is K random, this Kolmogorov complexity is now is greater than X, but it's also smaller than C, because we just defined a program that outputs X, right? And the length of that program is C. But now we get the contradiction that C is actually smaller than X, like strictly smaller, because that was our condition in the program for outputting X. So that's like the undergrad exercise for showing that diagonalization against Kolmogorov complexity. Okay, but crucially here we need structure of the actual real Kolmogorov random strings. Namely, we need that there exists infinitely many Kolmogorov random strings. Otherwise, if there are only finitely many, they could all be smaller than, like shorter than C, and then our program would never terminate, and there would not be no contradiction. Okay, so why does this approach fail for the KT notion, for Levin's notion? Where recall that we charge here logarithmically for the runtime. I just adjusted this for the sake of the presentation to be longer than the minimum runtime. Right? If you produce X, then you need to run at least the length of X steps. So that's like the minimum runtime of any program that could produce X. And now we do the same strategy and we adapt the output condition. Okay, so here we, in particular, we don't require longer than C, but longer than C plus. Okay, let's start at the beginning. Okay. So where did we start? Left off. Okay, so. Okay, yeah, the idea was, why does the canonical undergrad strategy fail for this Levin complexity, right? We do everything, essentially, we just adapt the corresponding bounds here, and then we try to see why doesn't it work? So the search strategy is essentially the same. We just iterate over all the strings in a binary tree. And we observe that at level L, this search strategy takes time 2 to the L time L, at least, right? Because we assume that this is a linear time Tm, and on level L, we have instances of length L. So we have 2 to the L instances and L time for each of the instances, right? And now we can see that if you consider a string of the next length, right? So you must have run through all of these, then we can just look at this equation and we can see that, well, the length of the string plus the log of the length of the string is always smaller than our bound that we compare against. And essentially, kind of intuitively, this is the reason is that we in each level we have to go through exponentially many strings. So this doesn't work, this strategy. Test? Okay. Yeah. So I just give you like a sneak peek into the actual diagonalization strategy that is used in the paper. So we assume that there's a linear time Tm against RKT. And now what we do is, if we are at the KT random string, which are denoted here in gray, then we go to the left child. So we just append a 0. And if we are at a non-KT random string, here denoted in white, we just go to the next value in the binary tree. So we take the integer value, add 1, and then convert it back into binary. Okay, so and that's just graphically how it goes. We are at the random string, we go to the left child. We are at the random string, we go to the left child. We are at the non-random string, we go to the right neighbor, and so on. That's the search strategy. Quite simple. And interestingly here, we need more structure than before. We need, namely, that there's a 1 KT random string. What is a 1 KT random string? 1 KT random means that there's an infinite string whose every single prefix is KT random. So for every prefix that you take of this infinite string, that string is random. And that essentially ensures that you never run into the right-hand border here of the tree. Okay, and I don't have any time to discuss the analysis, unfortunately, and it's also quite technical and boring. But that's the high-level idea. Yeah, and then the results are essentially MKTP is not in linear time. You can extend it slightly to be slightly more than linear time, and you can even allow for some false positive error. I don't have time to go into the details, unfortunately, but just talk to me afterwards, I can explain it to you. And then there's some conditional results as well. Namely, either it's in time t or it's not in linear time, but you can tolerate some false negative. And false negative is a bad error. We don't want false negative error. But if in this conditional result, you can also tolerate some false negative error. And for the crypto conference here, I also included a consequence, namely, if MKTP is in P, then there's some weak notion of a one-way function against deterministic algorithms, against deterministic inverters. Okay, and that's it essentially.
If not, thanks again.